So we're really glad to have Yevgeniy Dodis, professor from NYU, just up the street from here, visiting today. So yeah, Yevgeniy, extremely prolific cryptographer in a huge number of areas, and has shown a good ability to jump in on, previously on randomness generation, on secure messaging and encryption, and now Yevgeniy has been saying he really wants to start researching blockchains. So yeah, really glad that we got him this summer.
Oh, great. Thank you, Joe, and thank you for having me. It's like I'm excited to have such a great, vibrant group so close to NYU. So this is like my, so this is joint work with Daniel Yost. This is our first venture into something kind of related to blockchain, but in particular, so I'll tell you about perpetual encryption or how to put a private blockchain on a public one. So I'll start with motivation. This is actually the thing that I will care most about, your feedback and your comments. Usually I'm all about like jumping right away in like cryptography and schemes. So there will be that towards the end of the talk, but I would be curious to see if our understanding of the blockchain space kind of makes sense. So feel free to interrupt, ask questions, and so on. So I'll have some motivation from the hopefully blockchain space, then I'll motivate the notion of this perpetual encryption, in particular that I will try to argue that for our application we need a new type of encryption scheme, and then hopefully towards the end we'll talk about schemes, open problems. Listen, I don't need to tell you that blockchains are great, they took over the world, they have all those cool things like smart contracts, they're decentralized and so on. But the question we ask is like, okay, assume you are a small company, I guess a16z deals with a lot of like startups or something like that, and I don't know, you just want to, I don't know, you like something about blockchain, you like some promise or whatever, and you want to deploy it in your system. So what do we do, right? For the internal use. So it's like some kind of private use within a company or something like that, not necessarily of interest to the outside world. So there are basically two options as far as I understand. Either you join some public permissionless blockchain already built. Let's say you write some smart contract on Ethereum or something like that, and then use it for your application. So the process, well, it's not that simple, but it's kind of relatively simple. People at Ethereum did all this ecosphere and all this hard work of building consensus protocols and things like that. So it's doable, but at least most of the public blockchains, they're built without privacy in mind, so everybody will know about your balances or whatever, things like that if they need to. So that might be undesirable. Alternative, you will build, this is really what you need, is some kind of private permission blockchain for your own company, like only for employees or something like that, with some kind of application. But maybe you will just build your own blockchain, read some cool papers, and I don't know, build your own thing. But that seems, so the pros, you will get your privacy and also this permission thing. You don't like any random people inside maybe your particular blockchain. But this is complicated, like building a blockchain which like runs, you need like servers, right? So we'll try to get the best of both worlds in some sense. So we'll say, okay, what if we can create a blockchain which is, well, on the other hand, it will be relatively simple. Maybe it will leverage an existing public blockchain. In fact, maybe the public blockchain specifically, they don't have maybe enough of their own use. They will just rent out the consensus protocol for other people, so you don't need to solve this hard problem. But it will be private by novel design, and more specifically, the goal of this thing is, not that I'm anti-snark, I'm very supportive of this thing, but somehow to say that I would like to put some kind of encryption, so more generally light and efficient cryptography without something super complicated on top of the public blockchain, right? So this is what we kind of do. So basically our goal will be a little bit opposite of the current trend. Currently, you try to build, take everything off the main public chain. And here it's like a maybe different scenario. There is a public chain, it has a lot of capacity. Somebody built a good one, but maybe not enough customers. So they rent out the public chain to like smaller companies or something like that. And smaller companies will share this one public blockchain to their users. So let's see how it will look. Right, so imagine there is this big public blockchain, and somehow you have this group of people over here, this Sesame Street characters who want their own kind of chat or whatever, something like that. There will be a lot of transactions. Most of them will not be for your chain, but these red ones will be for your sub-blockchain, right? And the way it will look like, just because you don't want to scan the whole thing, each transaction on your thing will kind of maybe point to the previous transaction and so on, and then maybe this is like Genesis block or something like that. So this is how it will look. So people, and these red transactions will be encrypted in some sense, so they will post this encrypted transaction on a public chain. The good news, you don't need to solve this consensus. Somebody did it for you, so that's great. You don't need to assume honest majority. You just assume somebody solved, the public blockchain problem. And I mean, doesn't matter what application, could be messaging, but let's say if you have like your own thing, maybe people inside your little blockchain will keep track of balances or whatever. So this is how it will look. So let's try to do the first attempt. So the first attempt to do it would be just to distribute a fixed key to all the members of the group, so only people in your group will know the key. And then, roughly speaking, whenever there is a transaction, let's call it MI, it can encode balances or whatever you want inside those things. And you will basically encrypt under this key. You will append to the existing ledger the transaction. The transaction will tell you whatever you need inside your application, but it will also tell you the pointer to the previous one, right? So it's like you can efficiently navigate your chain kind of backwards, right? So does it make sense? So this will be like a toy high-level idea. We'll see what's wrong with this idea and some who eventually get to perpetual encryption. Okay, so all right, so this is the thing. So what are the good things? So because somebody solved consensus on the public blockchain, basically you have this unique linear order on the public one. Implicitly we'll get unique, well, we'll revisit it, but you will get this consensus for the members of the group. You will have consensus inside your private blockchain. And to the outsiders, what we care about, we really don't want people to know how many transactions I might think. It's like none of their business. So I really would like them to, this ciphertext should look like random strings. If it's not for you, if you're not a member of the group, it will be just random. Yeah.
In your previous example, so are you also want to consider some internal parties revealing the messages in the plane?
Yeah, some of this external functionality will be possible. For now, I will only want this thing. For now, we will talk a vanilla thing. It will be possible by simple extensions of our scheme. But for now, the vanilla thing, I want people to join and leave this group, and that's why we'll see the fixed key will not be appropriate. But for now, let's say you should be able, one member should be able to invite another member.
No, I'm asking whether some internal party can reveal the messages that are already encrypted in the plane.
For now, no. Let's say for now, very basic thing, right? As I said, it's like a new space. So if people like it, if it takes off, I'm sure there will be a gazillion of extensions about things. Very vanilla thing, right? Let's focus on vanilla thing just to support this dynamic group of people who can join and leave this private blockchain. So if you're a member, you will get consensus and you will understand things and you have a consistent view. All the members will have a consistent view. All the outsiders will have no clue what is happening. Okay. So there are some challenges, and I'm actually the next few slides will go through these challenges one by one. But so I'll just mention the words and then we'll go systematically over these challenges. Like how to prevent double spending if we talk about transactions and things like that, how to prevent related question, how to prevent forks. And here it will be very different about the distinction between fooling existing parties that will be easy to solve, and much harder problem will be about newly joining parties, how to prevent forks. Access control, it turn out, will be easy. Kind of group management, how can you add and delete members to this who have access. And the hardest part really in this whole kind of thing will be how to do it with metadata. Not just the transaction privacy, that's easy to encrypt, but some of this coordination thing, what period it is, what is operation, and things like that. We will really want to protect this metadata privacy, and that will be the hardest part of it all, yeah.
How much metadata, are you trying to hide the existence of this private blockchain, or are you trying to hide the number of blocks and when they get published?
So on a technical level, and you can tell me what it implies, on a technical level, if you're not a member of the group, and there is something, so basically, if you're not a member of any group, or you're a member of like 3 groups, you just monitor, scan the public blockchains, there is a transaction, you'll say, is it for group 1? No. For group 2? No. For group 3? No. Otherwise, it's a random string for you. That's all you know. So this is a concrete, nothing else. It's like, oh, this is for this thing that I'm not a member, and this is 17th transaction. Nothing. It will be very strong, like as strong as possible. And so let's try to go, this will be very basic, so it's kind of, you see that I'm novice to these things. I will go through some very basic things in that just to make sure that you guys see that we are not totally crazy. So let's just try to start with how people solve various problems on public blockchain versus, and then we'll see how to adapt it to our setting. So double spending, usually let's say this cookie monster has 100 cookies, maybe it ate all the cookies, but now it tries to give 50 cookies to Oscar. So, well, how do you do it in a public blockchain? Everything is public, everybody keeps track of balances, somehow people will complain. I mean, everybody knows all the balances, so it's easy. So here we are not going to reinvent the wheel, so I want to be very particular. In that, when I say about private blockchain, inside the blockchain, for now, the members will know what is happening. It's just they want to protect it from the outside well. So we don't need like, what Zcash does or whatever. So here, basically, the way we'll do it, we will adapt it to saying everybody inside the group, right? The authorized users, they will keep track of balances, so it's not going to be possible. So here, nothing really hard is happening. We are doing the same thing, we just adapt it to inside the group. But if you think, so with each of those things, there will be something obvious, but then we'll translate it into a requirement. And then when we sum up the requirements, I will argue that no encryption scheme supports this environment, requirements, and we will have to build something new. So one requirement is here, the joining parties might also be efficiently, if somebody opens them, whatever they think, invites them to join, they should be able to somewhat efficiently deduct the balances. So in the current public blockchain things, if you, let's say, only trust the consensus mechanism, but you don't have the slide clients or whatever, you basically need to spend the time proportional to the size of your chain. So here we will be okay with solution which is proportional to the size of your private chain, but of course this could be much smaller than the public chain. So maybe you can scan public blockchain, but it would be really, one cool thing we'll do, we'll actually achieve this, as opposed to if you join, scanning the entire public chain, which will have gazillion of channels not related to you. So we would like to be only efficient in the current, in your chain, yeah.
Are you actually preventing double spending as opposed to detecting it?
Well, I mean, it will be the same thing, right? It's like, there is like a subtle thing. So on a public chain, because minimum, a lot of people post transactions, if somebody posts an invalid transaction, that's actually a subtle point, it will still go on the public blockchain. It's just internally for people in the group. I mean, we'll see how they will kind of pretend it doesn't exist. From their perspective, it's like a garbage kind of transaction. So inside of them, I don't know if you call it prevent or not, but people will pretend that it doesn't exist. But on the public one, it will still appear. As, yeah.
I mean, we don't know how this scheme works yet, but you could conceive of having zero-knowledge proofs that the blocks are actually well-formed and don't have double spends, and then the public blockchain would never accept them.
Yeah, so I would like, you can view it as a feature, so I view it as a positive. We don't use any zero-knowledge proof, so I view it as a positive. Justin, Natal, you guys did amazing job with this, but, it's too complicated for me, so we'll do something simpler. So you can use a positive, but also it's like, now I think public blockchain doesn't know. People who run these things, they don't need to be like arbiters or what could post. Sure, people can post maybe garbage, but maybe there will be some gas or something spent. So if you put a lot of things, you just waste money for no reason. But yeah, there will be nothing like that. Public blockchain doesn't know about anything.
Well, yeah, I think.
And we'll use no zero-knowledge proof.
Yeah, that makes sense. That maybe it's much simpler. Like there would be a benefit to being able to prove the blocks posted were correct, because then it would simplify life for all your clients a lot, because they wouldn't have to detect double spending and ignore. They could just accept anything that makes it to the public blockchain has been kind of pre-checked for double spending.
Yeah, but as I said, double spending, now I think it's a trivial problem anyway. So I'm saying whatever solution you want, so our architecture will be friendly to this thing. If you want your message MI includes zero-knowledge proof, sure. So basically, right now, think about it. Whatever you can do on a public thing, we'll see how can we adopt it. So if the public chain supports what Joe says, I think we'll be able to support it also. So in particular, but we don't have to. Yeah. So one thing that we will do is we will want for new members to only spend time proportional to the, to their kind of chain as opposed to the whole public thing. So that's a subtle thing. All right, so this is the really heart of it. This is one of the bigger challenges about forks. So on a public blockchain, right, so this gives all the cookies to Elmo. So now this other guy whose name I forgot knows that this guy doesn't have any cookies, right? But now imagine you try to do a fork on a Carl thing, and there is like a completely unrelated transaction over here. But the point is, like, this verifier on this fork doesn't know that this guy spent all these cookies, so that's kind of undesirable, right? It creates this inconsistent view of the world. So how do you solve it on existing things? That's, of course, the whole thing of consensus protocols. You, like, longest chain, like proof of stake, all those kind of complicated things, right? That's what, you know, you need a consensus protocol. Another thing is, the point is somebody already solved consensus protocol, but so how does this problem appear? So this is an important few slides just to kind of see how we envision dealing with forks. So for existing members, relatively easy. So this is Elmo. Some could, let's say, inductively, there is a valid transaction A. It's posted somewhere on the public blockchain. Elmo is happy. And Elmo keeps track, existing member always keeps track to the last valid transaction in the thing. Then time passes by. There are all these not garbage, but transactions for other things that somehow Elmo ignores them, says, not for me, not for me, not for me. Now there is a transaction that he can decrypt, right? But this transaction that he can decrypt will also point to supposedly a previous transaction in the current thing, right? It will have this pointer. So Elmo says, oh, the pointers match. I can decrypt. I mean, maybe do the verification. I mean, if the verification, whatever, outside of our application, if something doesn't match internally inside the message, you can possibly reject. But here, in terms of, let's say, assume the messages are valid, you check the pointers, and he says, oh, it's a valid transaction. I move forward, and now I remember the address of the next valid transaction. Then time goes on, there is another valid transaction, the pointers match. You know, the green pointer matches a black pointer, is good. Now somebody tries to put in a valid transaction, right? So let's say it's possibly a member of the group, so this transaction actually decrypts, but you know, the transaction cheats. Maybe you try to create a fork, C prime, so this is like a logical fork, and this is how you would look on our public blockchain, right? So this posts a different thing. So for Elmo, it's not a problem. So to Joe's question, the public transaction will, the public chain doesn't know. It still goes on the public chain, this C prime. But Elmo ignores it because the pointers don't match. He was like, oh, it's like, I don't know, somebody is trying to cheat. Maybe you have a punishment mechanism, maybe not, but Elmo just ignores it, right? So this is an invalid transaction. Then this cookie monster or whatever, the Oscar guy tries to put another valid transaction. So it tries to extend the chain here. But again, Elmo says, listen, this points to C prime. I mean, just ignore it. And if there is finally a valid transaction D, Elmo is happy, and he updates his pointer here, right? So this is, okay, so this is how we envision this fork for existing members. And the cool thing, you don't need to worry about, longest chain or whatever. The consensus is already solved on the public chain. So you just do like totally trivial common sense thing, and you're happy. Does it make sense? Because the next thing will be a little bit trickier. Okay.
So the only question is the fidelity of a blockchain is a little different. So like C and C prime could be in the same block.
Right. Yeah. So here, I mean, they could be in the same block. I'm just saying, yeah, it could be. So here, you're right. So here you can think they could be in the same block. For now, I ignore this. I don't think it makes a difference. But
so you just assume there's an ordering within the block, and then whoever gets there first.
I'm saying C prime, whatever they're saying, if C prime takes multiple transactions, that will include all the multiple transactions. But whoever puts them, whoever is a miner who puts them, they have to point to the previous block inside your current blockchain. If they don't do it, you ignore it. Right? So if somebody tries to really create a logical chain for a new member, which is what we get next, they will try to put those things, right, for a new member. Right? So my point is, for existing members, it's basically easy. Right? So this C prime, D prime, existing members will really ignore it. But this fork is really meant, this is my next slide, so what about new members, right? So now assume the Oscar is the one who puts those C prime, D prime for this Zoe, okay? For the new member, and he invites Zoe, maybe gives the secret keys or something like that. So he really created an alternative reality, right? So he doesn't want Zoe to know about C. Maybe he spent like $1 million inside C. He doesn't want Zoe to know about it, okay? So what are Zoe's options, right? So this is like where slightly tricky stuff begins. So hopefully I'll explain it, right? So when he joins Zoe, he doesn't tell you. He says, oh, this D, ignore it. It's like garbage or whatever. It's like this is a last block in our transaction is D prime. In our ledger is D prime. So what can Zoe do, right? I mean, he gives, maybe Zoe knows the Genesis block or whatever. So what can Zoe do? Zoe says, okay, it looks cool. It points to C prime. It's like, well, okay, let me go to C prime. It's like, okay, it's cool. It points to B. It looks fine. It looks fine. Oh, it points to the Genesis block. Looks like a valid chain, right? So Zoe kind of has no option to, to do something, right? So it looks fine, right? Basically, the issue is just for following pointers, which we want to do for efficiency, right? For efficiency, we just want to follow pointers. Zoe cannot really know about the C because to her, Oscar says, listen, ignore it. This C is like random transactions for some other chain, right? So she has no chance, right? Is it, at least for now, right? Is it clear that Zoe has no chance? All right, good. But it's even worse. If you go back to the beginning, now let's say when Zoe actually moves now to D, now there is a next really valid transaction D. From Zoe's perspective, this is an invalid transaction. It's like, it means like D is pointing to some garbage. She's like, wait a second, this is my last thing. Why am I doing this? So it's actually kind of worse. It's not like Zoe upon joining sees the wrong chain, but when the right chain is extended, Zoe ignores it. Right, just like the honest members do. So basically, once you join the member, you give them alternative futures, the alternative future keeps growing. Yeah.
So when there's this new transaction D, right?
Yeah.
They could trace back to C and then trace back to B. And then they realize that C is before C prime.
Thank you. That's exactly what happens next. So good. So let's see what happens next. So what can we do? I mean, it will be actually 2 slides from now, but I'm going to answer your question exactly. So what is the naive solution? So the naive solution is Zoe, I mean, if she knows the Genesis block, because to her everything looks like that, it seems, but we will do something different. It seems like one thing she can do, she can like scan the entire public blockchain, right, when she does these things. And she will kind of see, exactly as you said, that C is prime. She can detect it if she scans the entire thing, right? But our goal is not to scan the entire thing and just look at the pointers. With just looking at the pointers for now, it seems Zoe has no chance, right? That's what I'm going to talk next. Basically, how can do it? So you are right, if you scan the entire, including all those white transactions, you can detect it. But that's too slow, it's possible. The good news, it's possible, but now it like means you need to trace the whole public blockchain, right? So how can we do better? So who can help Zoe, right? Let's see, let's look at options. Outsiders cannot help because they don't know anything. Everything is pseudo-random ciphertext, there is no data. So outsiders cannot help Zoe. So what about Zoe herself? To the best of my knowledge, I thought about using snarks or whatever. I don't know even solution with snarks. Even, I mean, we will not use any snarks. We'll be like super simple in what we do. I don't know how to do it because those white transactions are posted by different members. How do you prove that? I mean, I don't know how to do it, right? So right now I don't have a solution for this. Would be cool if you have something. Yeah. So Justin, tell me if there is some snark-based solution here. I don't know. So I guess Joe's solution might work if somehow you reject the original transactions at the origination, yeah. But this requires public blockchain to have cooperation, so maybe there is some way to do it.
Yeah, I mean, the way to do it, you would need the public blockchain to be verifying something about each block that was...
Right.
You could prove in zero knowledge that you're posting a block that is not a fork.
But yeah, so maybe, but it leaks, presumably it would leak, right? Because ideally, I don't want even the public chain to know for which transaction this, for which subchannel it is. Conceivably, with some limited privacy laws, you can do it. So we'll try to do something slightly different. So this is what we are going to do. I mean, let's see if, tell me if this is crazy or not. So this seems kind of hard, but what about existing members, right? I told you for existing members, it's easy to detect the forks because they were there from the beginning or something like that. So can existing members help Zoe and how? And the answer is yes. So let's try to see how they can help. So this would be our kind of assumption in this new model for this fork. At each point, we will assume there exists at least one honest member, maybe online, who will anyway, you will assume that this is like a useful channel, useful sub-blockchain you're building. A lot of people will maybe, monitor it and do things like, so you kind of assume that if somebody puts an alternative reality, which is easy to detect by existing members, at least one of them will be kind of maybe online and put some kind of complaints, and they can post on a public blockchain within a reasonable amount of time. And before, I mean, you can say, oh, this is like crazy. We don't want to trust anybody. Of course, if you look at the existing, blockchain, they assume much, much, much more, right? They assume to build consensus mechanism, you need like honest majority of people, like this miner. So here just need like one guy, right, to be there. So if you like compare what we are going to say with like you build your own in-house thing, it seems to me that this is you need to assume much, much more, right, to build the consensus. But he will just assume, kind of one honest party. So this is Elmo. So Elmo is the honest party. Let's see how Elmo can help Zoe. He doesn't even know Zoe exists and that Zoe will be joining later. But now there is this invalid transaction C. Elmo detects it. He was like, oh, I can decrypt something. It's decryptable by my key. But for whatever reason, somebody is pointing to the future. I wish I could remove it, as Joe says, from the public blockchain, but I don't want to burden the public blockchain. So what can I do? He can put, like, within a reasonable time, some complaint mechanism. And among the proof inside the complaint, he will actually say, you know what, hey, it's for my channel. I'm just putting this. Somebody is putting, maybe in the block. He will point the block, but basically he will put a complaint which points to the right last block. Right? They will put a transaction where is a reasonable time. And the same these things they will do for D. Like when you see invalid transaction, and I mean, there could be some, I'm not solving it. It's like how to, you don't want like gazillion of people put this complaint. So, I mean, this I leave outside the model for now, but at least some who will post a complaint. So now let's look at the Zoe. So she joins here or whatever. Somebody else, this guy, Oscar, told me this is the latest thing. She says, you know what, let me hang on for a little bit. And let me see if there is a complaint shortly by, right? Somebody gave me some kind of state. Let me see if there is some kind of complaint shortly after. And if there is a complaint, how do we resolve it? And this is exactly what you're going to do, but in a more, without scanning the entire chain. So how we are going to do? We can say, okay, so the green guy, the Oscar gave me one reality. Oscar gave me over here, and there is a complaint mechanism which points to this C. So let me follow these complaints until we reach a common block B, right? Or something. I mean, or possibly even to the beginning or something like that. And now you can see which branch is earlier than the other. So in this case, you can see, wait a second, after the common block, the C prime happens afterwards, right? So this C prime is, this is a valid one, so this is a valid complaint, okay? Then you can put more information to disambiguate it, right? So this is kind of the high-level idea. In the paper, we don't really address that much, the complaint mechanism and things like that, but we'll more focus on the encryption part, what kind of encryption you need. But, right, so this is the point. The point is, for Elmo, it's easy to detect forks at the latest state. So this is a high-level idea, but there is a complication, right? So this is the idea how we, but now if we want to say how we do it, here is a more complex thing. So in this case, it was pretty easy because C prime was in the same epoch and C, right? It's like it was kind of alternative future, but what if it's like the real chain went much further? A lot of members joined and left. So this Elmo already knows kind of the key for this period H. Maybe they already forgot the key for period C. I don't know, we'll see what we need, right? So now, is it obvious for Elmo to still detect this C prime, right? C prime is like for many epochs ago, maybe a year ago, like maybe the Oscar said, oh, this chain is like dormant for 1 year or something like that, whatever, right? So it's kind of not obvious. In particular, here is a requirement. The requirement is that Elmo must be able to detect and decrypt messages even as the fork is of a very old state, right? So Elmo should be really able to detect this C prime corresponding to B, even though a lot of stuff happened in between, right? So is it clear? So this is like, and as you'll see, it will be cryptographically challenging to do, okay? Any questions so far? Okay, last two challenges will be a little bit easier to solve, but yeah, if you guys, this is like one of the half of the difficulty of what we're going to achieve is here. So if you guys, right? So jumping ahead, when the group membership changes, keys change, it's like non-trivial for Elmo. It's like we don't want Elmo to keep all the keys for like A, B, C, D, E, F, G, and stuff like that. We want like some compact state. All right. So group management will be much easier. So I'll go through Inviqua. The native solution uses a static key for encryption. But of course, what if we want to remove members from the private blockchain, right? So for example, maybe, this, whoever we remove, Cookie Monster is like removed. So in the current thing, we will assume, and as I said, I'm open to other things. We wanted to have something simple that works. We will assume a semi-trusted group manager, probably the person who started the group. As we'll see, it will be semi-trusted. But basically, we'll assume there is a group manager who handles additions and deletions. Anyway, you need some access control to the system. So we'll assume it's like some manager of the company will control who has access to the blockchain. So this green guy Kermit is going to help people get this key. So somehow, whatever this key K prime is, we will assume there is a dynamic group of people, and this Kermit will help legitimate members get the new key. Right? But the key in particular has to change because we don't want the cookie monster to even know what this transaction D is for my chain after it's decrypted, right? So we'll need to solve it, but as I said, that will be relatively simple. But what it translates to our requirements, the encryption scheme must support key rotation, right? That's basically my point. You cannot keep the fixed key because if people are deleted, they should be like outsiders, right? So you cannot use a static key. That's all I want to say. All right, and finally, the privacy thing. We want the encryption scheme to hide transaction contents from outsiders of the group. And in particular, the metadata is also, it's not just the message content, like who sent money to whom, but even what is the period, what is the group. I don't want to hide, to leak anything. So the transaction should look random to outsiders, members of other chain, and even former members. So for example, here, imagine there is another pink chain, right? So this is a pink chain membership, and this is my blue chain membership, right? Possibly not overlapping, well, but let's say non-overlapping for now. So people here, Elmo, who is part of this guy, but is not member of the pink thing, if he looks at the pink transaction, all Elmo knows it's not for my thing. It's not for the blue thing. I have no idea if it's a random string. I have no idea if it's nothing, right? Also, if it looks at this 2 and 3, he cannot tell, is it for the same pink channel or not? There is no linkability thing. And this should be also held even if Elmo was member of the pink thing at 1, but removed in 2 and 3. Right? Is it clear? So this is kind of the notion of privacy that we will want. So what translates to requirements? The ciphertext must not include any channel identifiers. Basically your user experience is you get something on the chain, you're a member of 2 channels, of two private, whatever, 1 or 2. You try for each of them. If it fails, that's all you know. Okay? No epoch numbers, nothing. Because even epoch numbers leak a lot of private information. If somebody leaks that this is epoch 2 for some channel, people say, wait a second, I know that all these channels are for a while. Maybe somebody published the Genesis block, you kind of know, right? So we don't want any epoch numbers. All right, so this is a summary of challenging, nothing new. But basically, these are the things from previous slides. You can read them, but this is exactly requirements for the encryption scheme from previous slides, that members must be able to detect and decrypt fork even for all states. Right? Ciphertext must not include any channel identifier, nothing. They should really look pseudo-random, and the keys should rotate. We should be able to rotate keys. So I claim that no encryption really solves it, and this is a primitive that we call perpetual encryption. We'll abstract this primitive here. So this was the introduction. This is like I was outside of my comfort domain, so I'm slowly moving towards my comfort zone. So if you guys didn't kill me so far, it's a good sign. But this is your chance before I move to my comfort zone. So does it kind of make sense? I don't know, high level, what we are talking about? All right. So let me slowly start moving to my comfort zone. So what is this perpetual encryption? Okay. So again, I'll try to be pictorial. So it's an encryption scheme for dynamic group of parties. There will be epoch numbers. There will be a lot of messages within the epoch. That's group messaging. Epoch really is when something changes. Somebody joins the group, leaves the group, so something like that. So this is we call them epoch, right? So this is how the group membership changes. Maybe this guy is removed, these 2 people are added, or whatever, right? So now if you look at the perspective of, so this group manager removes the cookie monster. So now, so membership is done by the group manager. For now, it's trusted, but we'll talk towards the end how to reduce the trust in this group manager. So we want post-compromise security that even the cookie monster has no clue about these messages now. He doesn't know it's for the group or not. This is informal, but I was just saying we want this perpetuity. So this is important. When cookie monster joins here, even he should be able to detect messages for epoch 1. When he was in the group. So this is opposite of what is called forward secrecy. So this is internally incompatible by design with forward secrecy, because if cookie monster is the one who is online when the fork is created with 1, he should be able to detect it. But also for Oscar or outsider, we want really strong anonymity. Outsider or removed party cannot tell which epoch a ciphertext is encrypted. It's much more. It really has to be pseudo-random, but the epoch number will be really the hardest part. Once if we do the epoch number, we get everything. Last but not least, we want it to be efficient, hopefully much faster than snark things, but we want parties to have sublinear states. So it could be like million messages of my thing. My state should be like short. I don't want to remember a million keys and also encryption, decryption must be sublinear. I don't want to say, oh, was it for epoch 1? Was it for epoch 2? What is for epoch 3? That's like too much, right? I want to be able to quickly see what's going on. All right, so this is a little bit, so this is semi-formal how it translates to security requirements of our thing. So correctness is obvious. There will be an there will be a sequence of keys, K1, K2, K3 for different epochs, right? For now, the group manager knows all the keys, right? And we want, if the message is encrypted under Ki, obviously the current epoch, basically it just means that it's like, if everything is fine, there is a message for the current epoch, everybody decrypts it. That's good, right? So that's one property. Pseudo-randomness. Even if the attacker knew all the previous keys, encryption under the next key looks like pseudo-random, right? Completely pseudo-random, no epoch number, nothing, right? So this is pseudo-randomness. And finally, yes, it ensures confidentiality of transaction, metadata. It's like much stronger. Basically, we get the strongest thing possible, maybe unnecessary for application, but we'll achieve it. And perpetuity, it's actually a little bit stronger than what I said. It's like you really shouldn't be able to create a fork even if you know all keys. For now, this is like for perpetuity for users. In the last 5 minutes of the talk, I'll augment it even to the group manager. But we'll get there. For now, it's like even if you know all the keys, you cannot augment reality. You cannot put like a fake ciphertext at some epoch I, such that if you tell, oh, Zoe, current epoch is I, please decrypt it, Zoe kind of gets it, but a future member, doesn't decrypt the same thing as Zoe, right? So this is a little bit subtle to see, right? So this is kind of what it says. It ensures the functioning of the complaint mechanism. And the important thing, of course, we definitely want it for honestly generated ciphertext, but you cannot even make up, even if you know all the keys, you cannot make up a fake ciphertext that Zoe thinks is cool, but a future member who might be in a much later state doesn't get the same message as Zoe and therefore complain.
The keys are updating every epoch, even if the group doesn't change.
Well, I mean, it's up to you. Even that's kind of outside. It's like whatever you want. Either you can do it like every day you will rotate keys. It's up to you. Or only when the group membership changes. So inside the group members, there will be some delivery mechanism which is kind of orthogonal to this thing. It's like, I'll point it on the next slide. But this is, you can do either way, whatever it's like.
And is there an attack where a new user joins and they're given an old key so they can't find
that's exactly
right
what
chain?
fork prevention is, right? So if you give the old key, so you can always give, I guess, so you can always, there is an inevitable attack that you can give like a valid, say the group is at epoch 20, you say, oh, the group is at epoch 5, but you give a valid thing at 5. But now these members kind of don't get any new messages. They won't be able to get a single new message because, and if somebody actually posts 6 prime, if somebody tries to extend this, the moment somebody tries to extend this old 5, they will notice. Somebody will complain, right? And they will notice, So, but it's, there could be a weakness of the model, but this is, hopefully, by the way, there are a lot of low-level questions which will still need to be solved, like this one. It's just I'm kind of abstracting the things which hopefully justifies that you need at least this encryption scheme. Maybe you will need more properties. But I hope these properties kind of make sense, but let me know if, but it's also excellent questions. It's like there could be some subtleties.
Can you repeat the perpetuality again?
So perpetuality, as I said, hopefully, as a paper, I think we might have even a stronger one. I don't know. It's like I'm just giving you the most interesting special case. You cannot come up, even if you know all keys, you cannot come up with a ciphertext and some epoch I, such that using the key for epoch I, you will decrypt it, right? But a future member, using a future key KJ, you don't get the same result as Zoe. Right. So this is kind of, in the paper we have both one directional, we have like even stronger thing, but this is, I think, enough for this blockchain application. We have actually an even stronger definition in the paper, but, right, so this kind of, all right. So let's move forward. So this is intimidation slide. I don't mean to go through it. So there is one point of this intimidation slide is when we wrote the paper the first time, we kind of submitted in a little bit rushed form, maybe didn't do enough thing. And the comments we got on the paper, it looks at people say, oh my God, it's like there is some mess going on. I want to read your paper. Let me kill your paper by saying that somebody else solved it. So basically, instead of saying, oh, why don't you use this? It's like, okay, it's if you want me to use this, tell me how it works. They don't tell you how it works. They just say, oh, it's like it's solved by multicast, it's solved by this. So basically they get this comment of like, well, it doesn't work. Anyway, so the point of this slide, and if you're interested, I'm happy to expand on any point. So yeah, green things are kind of these unique things that our scheme definitely, well, and also this red thing. So green thing usually means good things, which is you see no other kind of, I don't know. This is a complete table, but basically we want post-compromise secrecy. Right? If you remove somebody, they cannot get it. We don't want forward secrecy by design. Right? It's like the inclusive. We want perpetuality, even that somebody joins, they should be able to detect like double spending or forks. Right? So this is by design. We want this perpetuity, which is new. And roster management right now, I abstracted that the green guy just gives a key and magically delivers keys to group members. But this is like an orthogonal problem. For example, using multicast encryption, we kind of sketched it. I think it's easier to combine it like black box. So I think roster management, you can use something called multicast encryption, but you can use other things. So this is an orthogonal problem which we are not touching in perpetual encryption. We really concentrate on these properties that I told you. Right, but as I said, it's just, and I can see the reviewers because like it's tricky. Somebody proposes something new, and it's like usually it's like there is a model, and everybody writes a paper which like increments the model. And this is like a very different model, so people say, I don't like to read this different model. Let me just say it's related to something without thinking. Anyway, so I think it's new, but if you think there is a different solution, let me know. All right, so let's talk about schemes, okay? And we'll see in the level of detail. So I'm getting closer and closer to my comfort zone. So I survived the difficult part. I hopefully survived. Let's try to build it. Let's start with naive attempt, and slowly we try to build it. So here is like the TLDR. I think our scheme will be, pretty efficient. Maybe not as efficient as conceivable. It's like it would be great to improve it and so on. But like no zero knowledge proof something. But there will be a couple of tricks. So it will be efficient, but not completely trivial. That's kind of, so let's see how to do it. So let's start with a naive scheme that this is a manager, and actually, this is a current group. You sample a fresh key, send it to the members. And this is orthogonal how. You can use multicast, whatever. It's like we are not solving the question how. Then the group membership changes. You send the new thing. So you send K2 to existing group members and K1, K2 to new members. Why do we need to send both? Because remember, we want perpetuity, so we want to be able to decrypt previous things, right? And so on. So an encryption is just a standard encryption. You just encrypt using KI as a message chain, and you put, maybe, so the ciphertext, you put the epoch number in the clear, and the decryption here is actually very easy because the epoch is in the clear. You just figure out, you say, oh, this is for epoch 5, let me look K5 and decrypt, right? So obviously this is wrong on multiple levels, let's see. So what is the issue? First of all, each party has to remember a key for every previous epoch. So that's bad. Also, the manager has to send linear size messages to new members. They have to kind of tell all the keys, right, to new members. And obviously, the epoch number is in the clear, right? So this is obvious issues. Let's try to fix them one by. Does it make sense? Sorry, it's like, yeah. So we're switching gears. We're going a little bit onto technical things, not super technical, but let's try to improve efficiency, right? There is efficiency and privacy issues. Let's try to just fix efficiency, and hopefully privacy comes for free. So the one thing, and this is again another comment, the only technical comment we got the first one submitted the paper, there was one person who kind of understood it. They suggested this solution, but unfortunately it doesn't work, but let's see. So there is this notion of delegatable PRF, which basically allows you to compress. So the way you will do it, at the bottom there are these epoch keys. This is the actual keys K1, K2, and so on. But they are pseudo-randomly derived from some kind of master seed. Every time you apply this pseudo-random generator. So if you know the key here, you implicitly can quickly derive the key for the whole thing. So at least if you want to store the whole prefix efficiently, let's say this is a prefix. If you want to store these 4 keys efficiently, you can just store the key as a seed for V. And then, so at the very least, this allows you, so each prefix, it's easy to see that for any prefix, there will be a logarithmic cover. There is like a logarithmic size kind of cover that covers all those keys. So at least if you generate these keys pseudo-randomly as a group manager, you can compress the storage of all those keys, so at least the storage is no longer linear. All right? And even decryption, if you know the epoch number, you will kind of, right? So this solves the first 2 issues. This solves the issues of linear sized messages and linear, right? So this solves these first 2 issues, which is good. Of course, what about anonymity, right? So the epoch number is still in the clear, right? So the epoch number is still in the clear. You can say, okay, you know what, let me just not put it in the clear. But the moment you don't put it in the clear, you have to do trial decryption. You say, yeah, great, I have a compact storage of all my secret keys, but I don't know, I get like the ciphertext, try it for epoch 1, try it for epoch 2. So this, as far as I can see, doesn't work because, I mean, you basically, if you do the storage and you solve, the moment you do anonymity, you kind of kill your efficiency, right? At least the naive thing. Does it make sense? And this is not our solution, but I just wanted to mention this.
Are you not doing trial decryption anyway because there's other people operating on the same blockchain? So every time you see a random string, you have to try and decrypt it anyway because you don't know whether it belongs to you.
No, but where I mean trial decryption is like, yeah, well, I have to do a trial decryption. I want to do a constant. I mean, sure. So when I say trial decryption, I want to do n trial decryptions, where n is a number of epochs. Yeah. So let's say there are just concretely like let's say there are 100 channels. I mean, you don't know the 100, but let's say there are 100 channels, and within your channels there is like million epochs, right? So when I mean trial decryption, if I'm a member of one channel, I want to basically do one decryption as opposed to million decryption, right? I'm not talking about 100 thing, right? So yeah, if you're a member of 3 channels, you will have to do 3 trial decryptions. If you're a member of 3 out of 100, new thing comes, you do 3 trial decryptions. What I don't want to do if I'm a member of a channel which has million transaction, and because I need to detect forks, sure, I can do one try decryption for my channels, but also remember, the whole complaint mechanism, it's important that if somebody tries to double spend and put alternative future, if I'm an epoch 1,000,000 and somebody puts something in epoch 3, I should be able to detect it at complaint. And in the naive scheme, the only way to do it, I will try to see, okay, is that 1,000,000 doesn't work. 1,000,000 minus 1 doesn't work, I'll have to go all the way back to 3 in the naive scheme, right? So we are not going to do it. We'll do something much more efficient, but I'm saying this particular way doesn't solve this problem, right? And in some sense, this is the hardest. Really, this flip, putting epoch in the clear, great, but anonymity is there, removing it, and trial decryption. This is really the key trade-offs that we are trying to solve. We want to get the best of both worlds, both efficient decryption and anonymity.
And you don't have any ideas about solving the other trial decryption problem?
Oh,
because that's actually a big problem in blockchain. Yeah. A lot of companies are
that's
facing
a great
that.
one. Yeah, not yet, but yeah, that's a great one. Yeah, I think in some sense that's what started this thing and kind of pivoted for this. This right now, for independent channels, it seems hard to compress it, right? Because these channels were created without any coordination. So somehow it seems to require that group managers maybe talk or do some kind of coordination. So I think that would be great. I mean, as I said, if you like this thing, it goes again as a thing. Everybody puts things into this, what is it called? Outside the chain. I forgot how they're called, whatever the Starkware or whatever this thing. We're doing the opposite thing. We're putting more things on the chain. But if you like these things, I can envision million of papers. I mean, probably not as influential, but million of open questions like this. But yeah, it's a great one. So this one we don't solve, but we will solve this one within the, right? So is it clear what we'll solve? We'll want to have both compact storage and still sublinear storage and decryption time. We'll satisfy the whole definition, formally defined, but really the hard part is sublinear storage, sublinear decryption time, metadata hiding, in fact, pseudo-randomness. And here is the thing, which was a little bit surprising. I said you can view it as a feature or as a bug. Right, but any sufficiently advanced bug is indistinguishable from a feature. I'll sell it as a feature. No, but so somehow the primitive, this perpetual encryption, right? It's like it's a private key thing. There is like a private group that stores things. You would expect you need keys, you need tools from private key cryptography, symmetric key cryptography, like encryption and so on. Somehow we will use public key encryption. I don't know, it's one of the great questions if it's required. I would conjecture yes, I don't have the proof. But basically, we will solve this thing using a public key encryption. Almost not completely as a black box, but we'll see. And as a free bonus, I'm going to define perpetual encryption only also as a public key primitive. I don't need it for the blockchain application, but because I need public key encryption to solve it, once I use public key encryption, I can make even the final scheme, final P, view it as a bonus. I don't need it for the current application, but I'm actually going to build a public key perpetual encryption instead of the secret key. Right, so that's one great big open question. Our scheme is efficient, more efficient than Snarks, but our goal is to, we will use public key encryption. So let me tell you a little bit of the syntax, but as I said, I will try to minimize any formulas or whatever, just so that there is, like for now, a trusted setup that generates a common reference string. Here is a manager's algorithm. First, it takes this common reference string and initializes its initial master state possibly some public parameters just for convenience. And then it can update it from epoch 5, it can go to epoch 6. And in each epoch, it generates a secret key and public key for members. And remember, as I told you, we don't need a public key encryption, but we'll just build a public key encryption, so for free, kind of, right? And people in epoch I will know secret key I and public key I, right? But or you can give public key I to the people from the outside or something like that. So users, they basically, there is an encryption scheme, given a public key and the message, you can produce a ciphertext, and given the secret key and the ciphertext, you can get the message, right? And for now, just to simplify notation, let's ignore these public parameters, just to make few letters. So this is like a super simple system. If you ignore this kind of stuff, which we technically need, but conceptually, this is a simplified syntax. The manager just initializes a state and tells, basically can incrementally produce this next public key, next secret key. Users at any point can encrypt and decrypt. So this is like normal public key encryption, right? For now. So, but of course, if correctness jumping ahead, it's important that this ciphertext C, let's say produced at epoch 5, you can decrypt it not just with the secret key of epoch 5, but secret key of epoch 6, 7, 8, 9, 10, anything, right? Anything in the future, but not the past. So any questions? Will be no formulas afterwards, or maybe fewer formulas. All right. So let's give the basic scheme. Okay, so this is like the basic scheme. Okay, so the basic scheme will be the following. The manager generates, for now, let's not worry about efficiency of the manager. We'll improve it towards later. It will be easy, well, relatively easy. Imagine the manager produces the entire key of public key pairs, right? Not secret key, public keys. And the epochs will correspond to the leaf, right? So the epochs will be at the leaves as usual. So this is like the usual thing. So let's look at the public key. So the public key for epoch 3 will be basically all the public keys, including the leaf, right? So this is a public key that, in order to encrypt for epoch 3, you need to know this logarithmically many public keys for independent public key encryption schemes. And encryption is just, so in encryption, you don't encrypt the message just for the leaf, but you encrypt it for all the parents as well.
Sorry, good question. So you generate all the public keys for all the future epochs ahead of time?
Yeah, so for now, ahead of time, so as I said, for now, think about this is like a bounded epoch scheme, an upper bound. I'll show you all these extensions will be possible. For now, I think there is a fixed upper bound on the number of epochs. I mean, yeah, that's, Valeria already sees the future. So the way I'm going to present it, I'll present like some toy scheme. It will not work, we'll fix it, we'll fix it, we'll fix it. It'll work, but for now, bounded number of epochs. Yeah, assume you know a bounded number of epochs, and for now, assume the group manager, the setup is like really slow. But we'll fix it.
Is this kind of the same as the old broadcast encryption stuff?
Yeah, it's all very related. That's why, so somehow it's like, I wish I could do something better, but that's what, like, when they got the comments, literally, nobody, like, looked at our paper. We didn't really get, like, we got only one technical comment, which was an alternative scheme which doesn't work. And everybody said, and this is completely accurate.
Your goal is different, but the construction works.
Yeah, so there will be, all those things, there are basically this tree is used almost in everything. GGM, pseudorandom function to pseudorandom generators, broadcast encryption is similar. So the tree is useful for multicast encryption. Almost everything uses a tree, and that's why people was like, it cannot be new. It's like it uses a tree, so everything using a tree has to be discovered earlier. So I feel like we discovered one thing where the tree is used in a slightly different way, but maybe not. I don't know yet. So, but yeah, at the end, it's not, as I said, view it as a positive, old idea, but details matter. But yeah, it's like, conceptually, yeah, we are going to use trees like broadcast encryption, traitor tracing, all those papers use trees in a different way, so we're also using trees, yeah. But you're right, it looks so similar that it cannot be new, but I couldn't find, yeah.
Will we have to worry about, like, an adversary does not encrypt M for every public key?
Yeah, absolutely. Well, you guys are too smart. So as I said, the way it's excellent, it's not even the first attack, it's the second attack, but yeah. So what we are going to do, just to say, I'm going to kind of try to, and that's why sometimes people hate when they take cryptography without, other classes. They hate it's like you start, it's like, oh, don't tell me the final scheme right away. So you're right, there will be a lot of issues, and we will hopefully solve them incrementally. But for now, let's just solve kind of efficiency issue and just kind of get a high-level idea, and then slowly we'll solve it. Good. So the first thing is, just think about correctness for now. Right? I just want to solve this efficiency trade-off between the storage and the trial decryptions. And then we'll talk about adversarial stuff. To encrypt, you will just encrypt separately for each level. Good. And so there will be those kind of ciphertext over here. So the good news is the length of the ciphertext is a height, so it's not constant, it's logarithmic, but hopefully not too bad. Epoch number, and the important thing, we don't include epoch number in the ciphertext, so technically we need our encryption to be anonymous, so it should hide the public key. So there is a notion of anonymous encryptions with many constructions. So encryption, public key encryption scheme will have to be anonymous. So that's easy. Let's go to the secret key. So this is a little bit new. I haven't seen exactly this, but it kind of makes sense. So the way to do a secret key, so if you're at epoch 7, you, as before, just like as GM, you want to cover secret keys from epoch 1 to 7. So this makes sense, but one thing, as I said, just jumping ahead, why we need public, I mean, there will be multiple reasons we need public key encryption, but it's important to encrypt to 7, you have to encrypt all these nodes. And nobody yet knows any of those secret keys. So that's why we need this kind of asymmetry, jumping ahead. We need to be able to encrypt to this node without knowing the secret key for this node, right? To encrypt for 7, you will have to do this. So nobody knows secret keys for these guys yet, right? So this is a critical place in our analysis or whatever. I think it's kind of essential, but yeah, it drove us nuts. We couldn't prove that you need public key cryptography. We couldn't avoid it, but anyway. Wisely, we didn't put it in the submission, because I don't know, hopefully wisely, because, anyway. But yeah, that's an open question. So this is, so compactly, even though, those keys are independent, but compactly, intuitively, this guy kind of covers this, right, intuitively. So how do we decrypt a ciphertext? So let's do it visually. So you have a ciphertext for epoch 3. Somebody encrypted an old ciphertext and you want to decrypt it. So you kind of try it level by level. You can say, okay, can I decrypt, sorry, this is like an honestly generated thing, and I'm trying to decrypt it with 7. So I will get intuitively, if I use what is called robust or some kind of appropriate robust encryption scheme, if I try to decrypt using this public key and a ciphertext for this one, I should hopefully fail, and we'll ensure it, of course. But yeah, you can imagine that a normal encryption scheme, with a little bit of extra effort, it's called robust encryption scheme. If you try to decrypt the ciphertext encrypting after public key 3 using completely independent keys here, you will fail. Okay, so great. Let's go one level up. You get this guy, right? So this is the next part of the ciphertext. You decrypt, you get an error, right? And finally, there is an intersection. It's magical, but it's by design, of course, right? There is an intersection at level 2. It's both green and orange. Now, both encryptor use this key, and this guy stores this key, right? So he decrypts it, and it succeeds, right? So this is a key. There will be many low-level details we need to fix, but this is a key trick to get our efficiency issue, which is good because within an hour, I told there's a key trick, and then the remaining time we'll solve little issues. Does it make sense? I'll pause here, right? So that's why you kind of encrypt those things, and then you decrypt, you partition the things. So the key point is there will be success. So the key point is, by design, it requires a little bit of proof, but it's not very hard to see that for any j greater or equal than I, there will be exactly one intersection point. If I is equal to j, the intersection point is, the intersection point will be exactly here, but otherwise it could go somewhere up the tree. Right? So there will be exactly one intersection point, but for the future, jumping ahead, there will be no intersection point. If somebody encrypts here, like for 8, no intersection, right? Anything in the future, there is no intersection, and anything in the past, there is precisely one intersection. So it looks like we are done. We are done in terms of efficiency, but unfortunately, in cryptography, we are kind of pesky people. We like our schemes to be secure. So unfortunately, this thing is not yet secure, but it's getting there, okay? So let's try to, does it make sense? So let me tell you the attack on this scheme, and then we'll slowly start fixing it. So I'll pause here. This is really the key idea, which I find cute. I haven't seen exactly this kind of usage of trees, but it's true. Yeah. Okay. So let's have the attack on perpetuity. So the attack is basically exactly as you said. Imagine that you just put a valid ciphertext in the bottom for Zoe, joining later, right? For this yellow guy joining later, and put garbage over here, right? So you just something like that. So then, looking at the cookie monster, he tries to decrypt. Doesn't match, and obviously this also doesn't match because it's garbage thing. So he will just think it's an invalid thing, and he will ignore it, right? So cookie monster will ignore it, but Zoe, who joins, right? This is like an inconsistent ciphertext. He will just ignore this thing. He'll say, okay, garbage, garbage, garbage. Nothing matches. It's not for my channel, or I don't know. He doesn't know it's not whether it's for his channel because he only stores these orange keys, right? So everything is garbage. But now look at poor Zoe. She comes here, Oscar gives her the secret key for 3. This ciphertext is valid. So Zoe actually is happy, right? So she is success, so you fooled, right? So Zoe joined thinking it's an epoch 3 and the cookie monster doesn't protect her, right? And our whole point is that the cookie monster or anybody in future epoch should protect it, right? Make sense? So it's so we do need to solve consistency, right? So let's try to solve consistency. Yeah, so she successfully decrypts. So let's try to look at the options. I'm going to give you 3 options where the third one works, the first 2. So the first option, you can say, well, let's make cookie monster work hard and kind of try to decrypt this. The problem is I don't know how to do it efficiently aside from storing all the keys and doing trial decryption, right? So this will be kind of not, as far as I know, I don't see how to do it efficiently. Yes, it would be great if cookie monster does everything, but I mean, Jaws, or if you guys have an efficient snark solution, maybe, but we'll avoid it. We'll do only lightweight stuff. Okay, so the other option is to give Zoe more keys. Maybe we give Zoe some of those keys over here that she can detect, right? Well, of course, that's not secure, because if there is, Zoe maybe is kicked out at this group, at epoch 4, she shouldn't be able to decrypt this part, right? So I cannot give her the keys up to 3 because it's not part, right? Because Zoe should only know these 2 secret keys, she cannot know this, right? So I cannot give her this. And that's where, of course, the public key encryption is. So the thing is, Zoe must be able to somehow reject this thing without decrypting it, right? Right. So in public key primitive, that's high level how public key primitive will solve it. So let me show you how to solve it on the next slide. Okay. So, but yeah, you can see why we kind of inherently need this public key primitive. Anyway, let me show you how you do it. Okay. So this is our basic scheme. Right, so in our basic scheme, I just expanded it. You encrypt and you use normal independent randomness for each encryption. So what we are going to do, we are going to not use independent randomness for each encryption, but we'll derive it in a pseudo-random way. How? So this is how. So let's watch this animation that my postdoc made. All right. So first we'll do it in 2 steps. First, let's in addition to the message n, let's encrypt for now a random seed. I mean, that doesn't hurt. It's like a useless seed. You just, instead of a message, you encrypt a useless seed for now, right? Okay, so that's, well, of course, that doesn't solve anything. But now, watch another thing. This random walks becomes a pseudo-random generator, okay? So what you do, at each level, the first level, whatever, you just apply it to initial seed. So you have the seed. But now, the seed that you decrypted the first level will be used to deterministically derive the next seed and the next randomness. So for those who know, it's like we're kind of running a stream cipher over here. And then this seed is going to be used to deterministically compute this, and that seed is going to be used to deterministically compute that. Right, so this is kind of non-zero knowledge, but this is kind of zero knowledge enough for exactly our purposes. So let's try to see if it works, right? I mean, it's not clear why the trick works. I'll show you in a second, but is the trick clear? So instead of doing deterministic randomness, I will kind of compute pseudo-randomness, kind of saying that if you have access to this, it's okay for you to kind of break this other ciphertext in some sense, right? Because if you're already given the key for this, it's okay for you to do this, but not the other way around. So let's see how Zoe will detect it. So she decrypts that ciphertext because she has this key. Now, this is our previous attack, this garbage ciphertext. So now a point that Zoe will immediately know that something fishy is going on. So she decrypts this thing. Now she decrypts the seed, and now she will try to say, wait a second, let me take the seed, derive the randomness, and let me check if I re-encrypt the message m, do I get this garbage? And I'm not going to get this garbage, so Zoe says, wait a second, I'm rejecting right away. So even though Zoe is only given decryption key for the bottom, as a sanity check, she checks the consistency of ciphertext sub the tree. Right? So now Zoe herself will reject the ciphertext. So the cookie monster cannot do it. He will reject it anyway, but also Zoe will reject it. So this is like a way without giving the secret key on a ciphertext per ciphertext basis. We give Zoe ability to check this ciphertext up the tree. So this check will fail, and I think, and this achieves, I mean, this is maybe a little bit technical, this achieves some weak form consistency, which is enough for our application, where we only say that it's impossible for Zoe to succeed and the cookie monster to reject. In the paper, we show how to achieve an even stronger one, but we don't need it for the blockchain application. Looks like we are done. We solved your consistency issue. Not quite, so we have to do 2 more steps. So what's the problem with this scheme? So we're kind of getting closer and closer to right scheme. So the problem is this kind of strong robustness. So here is an attack on the robustness scheme. So imagine, there is Zoe in this epoch 3. She has the secret keys, and Cookie Monster has these secret keys, kind of, right? The purple secret keys. When they do the trial decryption, let's say they do this trial decryption at the second level, right? So it's important, remember, the ciphertext could be malicious. So it's conceivable that somebody who knows, let's say, all the keys can produce one, malicious ciphertext which kind of decrypts differently. So implicitly, when I said robustness before, kind of implicitly I meant like honest robustness. Like if you just honestly produce ciphertext, they will be decrypted. But here, remember, we need this, what is notion of strong robustness. So weak robustness, so normal robustness for encryption scheme, if you just encrypt honestly, kind of you will detect if you encrypt under two different keys, the second one will not decrypt. But here we need it even against the maliciously generated ciphertext, right? So we want to make sure that it's impossible to produce a single ciphertext such that when Cookie Monster tries it and Zoe tries it with honestly generated keys, they will get both valid answers, right? Makes sense? Sorry. It's like it's almost the last technical kind of thing. There is just one more. And so here is a trick implicitly in a slightly different constant. It's in a previous paper. We discovered it independently, but we are happy to attribute it to them. So here is what you do. So previously, remember, we just encrypt the message and the seed. Here is what we do. We are going to also, as part of the ciphertext, we're going to do a commitment to the epoch number. We're going to commit to epoch 5, just one more component of the ciphertext, and this is decommitment information, Z. So we're just going to encrypt the decommitment at every level. Right, we're just going to do this commitment at every level. And now, if you look at this Cookie Monster, maybe there is a malicious ciphertext. Maybe it will decrypt here. But once you get the Z and compare it with the commitment, you will see that this is not on the path. 3 is not on the path. This number 3 that will be here. So in order for Zoe to encrypt, this Z has to decommit to 3, to this epoch number, right? Because Zoe will only accept if, this is like for epoch 3. Right, and this Cookie Monster will reject it even though it decrypts, but the decommitment doesn't match. So this is like almost the last technical fix for this thing is just how to achieve the strong robustness because we care about maliciously generated ciphertext. And again, our goal for the whole thing is to avoid like zero knowledge, snarks, kind of lightweight stuff, right? So we are trying to use only lightweight stuff. Good, we are almost there. Unfortunately, it's still, it is secure. So now this is secure, but only for what is known as chosen plaintext security, which just means encryptions of anything is like pseudorandom, but the attacker doesn't have things. So for this application, it's probably not enough. For blockchains, we want like some kind of non-malleability or whatever. More specifically, we want chosen ciphertext security. So now the question is, can we do chosen ciphertext security with this basic scheme? Let me put the scheme before. And of course, the first thing that comes up, you can say, okay, use non-malleable commitment, whatever, and use chosen ciphertext secure encryption. Instead of chosen plaintext, let's use chosen ciphertext, right? So that's a trivial fix. Unfortunately, this fix doesn't work. Here is an attack. So for those of you who don't remember, chosen ciphertext security means you get a challenge ciphertext and you allow task decryption for any different ciphertext. Anything else, and it shouldn't help you. So here is a challenge ciphertext, commitment C1, C2, C3, C4. So here is what you can do. You can just, replace this by garbage and ask Cookie Monster to decrypt. Right? In this thing, you can choose any party who can decrypt. You can say, I take this challenge ciphertext, but I can ask a future party who is Cookie Monster. And the Cookie Monster will only be able to decrypt this component and will have no clue that I changed this component, right? So basically, if you just encrypt independently, those components are not tied together, so you can just replace one, right? So what do we do? The idea is to include a hash chain of the ciphertext. So there is like something very efficient. There is like something called, just you hash. So the way you build, you hash a long message, you just hash it one by one. So basically, this is a pseudocode. Roughly speaking, we had 3 components previously: message, the seed, and this decommitment thing. But we also include the current kind of hash chain. The details, so basically you just can use this hash chain where you hash the previous thing with the next ciphertext, you commit kind of to all the ciphertexts. And with this thing, so the high level idea is now, let's look at this attack, right? So he will decrypt the C3, it will give him a hash chain, but the hash chain commits to the previous ciphertext, right? So basically, he can recompute H3 because H3 is just deterministic hash chain. Starting with a commitment, it just recomputes the hash and sees that the hash doesn't match, and he will refuse to decrypt. So again, it's a cute little, sorry, I don't expect everybody to follow, but it's like very simple. The point is to just include an extra hash. So once again, like if people are looking, let me just see. So the attack was that Cookie Monster can only decrypt this 3 component. How does he notice that we change this component, right? To random and therefore break chosen ciphertext security? Well, the Cookie Monster will figure out the hash chain, this value H3. He can recompute the hash chain up to H3 and check it. So if this thing change, in the challenge, because C3 is CCA secure, you cannot play with H3. You have to include honest H3. If you change this, the hash chain will not validate. So basically, by making the encryption scheme, individual encryption scheme CCA secure and using the hash chain, we solve everything. So now it is secure. Okay, so we're in good chance. But it's only outsider secure. Okay, so this is, and as I said, so my goal is like kind of give you the TLDR. We try to have a problem. Hopefully, it kind of makes sense. We wanted to build it to solve it in a strong way. And the thing is, it wasn't completely trivial, but there are these little tricks which are cheaper than I think zero knowledge proofs, which I think works and hopefully solves this whole problem. So let me tell you, this is literally the last thing. It's like, what does it mean outsider security? So far, we assume that the group manager is honest. So in particular, we implicitly assume that all those keys that the Cookie Monster get or whatever, they're all consistent. There is like no, right, so the key evolution. So the Kermit gives people consistent keys. So the question is, what can be done against a malicious manager if the manager is like not trusted or something like that? Well, obviously, they can add and remove people at will. We cannot protect this. Confidentiality and pseudorandom, well, we're never going to exclude the group managers and all the keys in advance. That seems kind of impossible. But what is possible is perpetuity, right? So namely, what we would like to do is that even a malicious group manager cannot, somehow has to commit to everything in a way that even if he colludes with everybody, he's the attacker, he cannot cause, the Cookie Monster not spot, basically the perpetuity property. That if you decrypt a future thing, if you can decrypt in the past, you have to decrypt in the future. So this we can protect, and this is what we are going to do. And this is a high-level idea, literally promise you this is the last technical idea, how to achieve the strong security is basically the group manager for now will commit to the entire thing using a Merkle tree. So roughly speaking, inductively, you will, kind of having inductively computing the hash of left and right, you will kind of compute the hash of the node to be the hash of left, right, and the current public key. So you basically do a Merkle tree which commits to all the public keys, right? And that you publish, the root you will publish in public parameters, which for now, you will publish it in the Genesis block. It's a bounded number of periods for now, right? So you will kind of do it. And for secret key generation as a minor thing, instead of giving people the secret key, you'll give them the randomness to generate the public key secret key. You produce this public key, and you check if the public key kind of matches. So basically, using Merkle trees, you force the group manager to commit to consistent keys, and when you kind of open it for people, right, when you give people their corresponding keys, you can easily prove kind of membership, so people know that the group manager cannot lie. And once the keys are consistent, it kind of works. There is like one problem, well, there are two problems with this. Okay, so one problem, which is actually a great open problem, it's like there are two problems that drove us nuts in this project. So far, it seems like you can use almost any public encryption scheme, possibly with anonymous ciphertext. But for this thing to work, we need it's a little bit subtle, but we need like a strong correctness assumption. And to the best of our knowledge, lattice schemes don't satisfy this assumption. So we don't know how to actually instantiate perpetual encryption from lattice assumptions for insider security. So for insider security, we currently don't know because, yeah, as I said, for the group manager not to choose, there is like a subtle kind of property that because of the noise, I'm sure it's solvable. I just don't know maybe enough lattice-based crypto to solve it, but that's yet another open question. So it's like, the openness of post-quantum is for a very unusual reason. It's like we need like a very strong correctness. And the other thing is like, it half solves Celera's question. It's like, how can, we want like the group manager to give you this kind of openings like incrementally without storing the whole tree. And there is like this cool sequence of crypto Eurocrypt papers which people don't really know how to do this Merkle tree traversal. How can you commit to a Merkle tree and always be like logarithmic size instead of storing this linear thing. So we can do it using these things. It's like a pretty cool thing. So we can use Merkle tree traversal to do this thing somewhat efficiently. But the final thing, which the current thing doesn't solve, is it's still bounded number of epochs. Even with bounded number of epochs, we can make the group manager kind of efficient, start with logarithmic state and slowly add keys and slowly keep constant state, but it still has to be kind of for now a priori bounded. So if we want an unbounded solution, basically, unfortunately, we need to use a hierarchical identity-based encryption, never mind what it is here. So just to check, so for outsider security, we can just make the height of the tree like security parameter. We don't need the strong correctness, everything kind of works. So we'll just do Merkle tree traversal for depths like 100, and 2 to the 100 is a good upper bound. For this insider security, yeah, unfortunately, because you need to like compute the Merkle root hash, we don't know how to do it. Well, we know how to do it more efficient than NISIX, than SNARKs, but not efficient, in my opinion, for practice using hierarchical identity-based encryption. So maybe go to pairing world or something like that. Yeah, so we have some things in the pairing. All right, so that's my next to last slide. Yeah, okay, so what is open problems? So these are like big high-level open problems, just kind of more applications. Now that you have one public chain and many private chains, can they talk to each other, right? Or something like that. Can you do transactions between private chains? You kind of open some, not the other. I don't know. It's like that, unfortunately, seems to go into the snarks that I'm trying to avoid a lot, but I don't know. Maybe you can do something else. Maybe also transactions in and onto the chains, possibly from the outside. Kind of unclear. For perpetual encryption, as I said, there is a super annoying technical reason why currently we don't have post-quantum candidates. Is just because of this insider whatever strong correctness requirement. More efficient scheme, we feel like the schemes are nice, but in practice, I guess, doing even, I don't know, like 20, 30 encryptions, maybe people will not like such big packets, right? So it would be nice, and especially for insider security, where we need like, you know, high hierarchical identity-based encryption. To me, that's the most thing that for symmetric, if I only want symmetric perpetual encryption, can I actually build it without public key encryption, even the weakest kind of thing? I conjecture the answer is no, but I don't have the proof. It's one of those, like, to me, it's one of those surprising things which looks like a symmetric key primitive, but somehow requires public key techniques, but I don't know exactly how to prove it. And obviously, yeah, if you find it, I mean, the secret is this work came up from kind of secure messaging thing. We kind of had some scheme, and then somehow we were looking like in jeopardy for application, and this blockchain came in the application. So it's not like I was like a blockchain guy and I was like thinking about it. Something came up in a different domain, and we just applied it here. So I don't know. Maybe there are some other applications. All right, I'll stop here.
Does the like group action-based PKE, does it satisfy the strong correctness requirement?
To be honest, we didn't check. So you mean like group action?
Like isogeny-based.
Isogeny-based. I don't know enough about isogenies. I would consider, yes, there is no noise in isogenies, right? Yeah, we need, there is like a technical definition of correctness that we need in the paper. I would conjecture yes, but we didn't check. I don't know how practical those schemes are, but yeah, it's a good thing to check. I don't know. Good question. Yeah, I guess actually good. So if, okay, his answer is yes, I guess that would be post-quantum. So yeah, we should definitely check, or I guess if, yeah, I can look up and we can check, I guess, you know, at lunch, whatever the actual definition of correctness we use. It's a little bit subtle. It's like one of those things, you write proofs and you see exactly what doesn't work, so you kind of go back to definition, change it. But yeah, it looks a priori like, yeah, it's like, oh, everything is generic, this minor thing, but then it's like, oh, let's do it in LW, and I'm glad we checked. It's like, wait a second, something doesn't really work.
Why can't you just put the last epoch key in the current block?
Last epoch key in the current block, you can. How will it solve it? I mean, if you, because alternative history could be, we are like an epoch 500, alternative history could be an epoch 3.
So you go, you register, I give you key 500, I point you at some block. You don't know whether it's part of a fork yet or not.
I see, and you get the previous key, yeah.
And you get the previous key in that block, so then you go back.
Sure.
And then you get the previous key again.
So
you have
so that will solve, at least partially, there could be some subtlety. That will solve the issue. So this is kind of an issue of multicast, like a key distribution, which is orthogonal to perpetual encryption. But with this issue, the decryption will be linear. So sure, I can try this, I can say, okay, it's not this, but if I'm at 500 and this is 3, I will have to jump for 97 to get this period 3. So the decryption scheme will be linear. The good news, using multicast scheme, which also use a tree in a slightly different way, it's like a lot of trees, but using multicast, so this is like a key distribution issue. Right now, we just assume Kermit gives you this magic key for group members. There is this primitive called multicast, which allows exactly this dynamic group management. It's like I can revoke somebody. There is like one group, and you can revoke and add people. So your thing will be kind of a naive solution to the multicast problem, but this is not our work. But we can use better multicast schemes, which, in some sense, they do something similar, but more aggressively using trees as opposed to paths. But yeah, I think this is, if I understand, this is right. It's a key distribution thing. We kind of assume for now the group manager is either honest or is kind of committed. Nothing I said is how to distribute these keys, but I think multicast will do it better than what you're saying. But I think it will work, yeah.
It seems like you started talking about blockchains, but this is back more to the motivation. Like you're really only assuming sort of a bulletin board that has a total ordering of stuff.
Yeah, that's my knowledge of blockchain. It's like, it started from the messaging. Initially, I was like, okay, let's look. The initial kind of application was more like, it's like you have this, groups on this bulletin, and people just talk, and then people says nobody cares about people talking on the public thing. So I had to throw some financial stuff without telling you what this financial stuff is. But yeah, we don't do anything about, or at least currently, it's like, on a technical level, it's just the messaging, and whatever mechanism you do for blockchain would work. Currently, the simplest one, you do whatever the public blockchain does. Whatever data structure you do for the public blockchain.
I guess I mean, like, you're not taking advantage of any programmability or like smart contract capability of the underlying chain.
Yeah.
I guess I wonder if, we talked about the zero knowledge. I wonder if there's anything else that you could use that for.
I hope so, yeah.
Because you could do this on Bitcoin, which is kind of interesting. Like, you don't need, it'd be very expensive on Bitcoin, but you could do it.
So you're saying smart contracts? Yeah, I'm hoping so. I would love to do, I know a little bit about smart contracts. I know high level how they work. My understanding is currently there are some private, you can emulate some level of privacy because you can just put commitments and people do some opening. So I think it would be awesome to incorporate, I haven't thought if there are any subtleties of smart contract. Currently, I would just say whatever public blockchain does with smart contracts, you can just put the smart contracts inside your blockchain and do whatever.
Okay, yeah, so maybe we're talking about two different things. Like, you could have your private blockchain have a smart contract. I think that would work fine. The users would just have to validate everything.
Yeah.
You could also take advantage of smart contract capabilities in the public blockchain that you're building on. And there might be some efficiency gains or other things.
That would be awesome. I think that would be awesome. It's like, for me, it's hard. Currently, I'm only learning about these things, so it's hard to visualize the whole power. I think I understand it. I would love to brainstorm about it. Because, definitely we didn't put enough financial. Yeah, that would be awesome. I think it's a great suggestion, yeah.
Subtle thing is, like you said, we're doing the exact opposite of Starkware and other layer 2s. But actually, the way they work is identical. You're actually doing the exact same thing that they do.
I thought I'm doing like anti-rollups. But
they have this concept of an inbox. So they just store transactions there, but the blockchain does, at the smart contract level, doesn't execute them.
Right.
And so what you've actually implemented is an inbox.
Okay.
And then the layer 2 just takes the transactions out of the inbox and does whatever it does with it. And then it kind of pushes back the results. But anyways, your application is immediately applicable to layer 2s as a sort of encrypted inbox.
If they currently don't do it, that would be amazing. If you, as I said, I don't know enough. That's why it's like I thought it would be a good opportunity to give a talk here. So I'm grateful for joint team for arranging the talk because I don't know enough. I have a feeling that this, it could be applicable for more things. Let's talk about. I think that's both the smart contract suggestion is interesting and. Yeah, and globally, I was kind of a little bit excited just to see. It looked, at least on the surface, we're doing opposite for rollups, but maybe it's actually not as opposite as I thought. So I thought it's like, listen, you probably heard like 100 talks, which are like really fascinating things, how to save like a factor of 3 here and how to do things more efficiently. In the whole thing, I felt like this could be a little bit of a different methodology. I don't know, like different kinds of math, different kind of tools. So I would love if it's useful. I would love if you guys, push it somewhere or, once, you find out the uses, we can optimize and so on. Yeah, smart contracts also would be amazing if there is a technical. Yeah, that's my feeling in general. Whenever you kind of do something, and when people from the real world who know about real world start to look at it, new problems come up which you don't think about it, right? So this perpetuity, to be honest, it came from, basically we had a scheme, and once we tried to formalize it and put the blockchain stuff, more kind of constraints came about. So, and luckily for us, they were not like that difficult, this hash chain and this and that, but they were kind of cute enough that you need to get them right.